Hello.
Hello, good evening, sir.
Good evening, Rakshit. Uh, are you able to see my screen and my voice is good?
Yes, sir. You are audible and visible too, sir.
Okay, we'll wait for a couple of minutes. Let's see if anybody else joins. Then we'll start. I think
Okay,
6:05.
sir.
Okay. Yeah, so I think uh, we can start now. Pradeep is here. Budit is also here. Anyway, we are already at 6:05, so I think we can start. So, yeah, as far as I saw the syllabus for this week, it was basically like problem discussion. One second. Yeah, I'm on mute. So, yeah, anyway, we have not discussed this uh, important part of fluid dynamics class in last classes, which is like related to Bernoulli equation. So, today we'll do that. We'll discuss about it. Then maybe some, you know, examples I'll take. One second. Yeah. So, this thing. Mm, like, have you guys had a chance to go through, uh, like, I mean, did you understand what is Bernoulli equation and all? Anybody, if you can uh, just tell what you understand by Bernoulli equation, that will be better. Anyone?
So the, the actually the this what is it called, the like the fluid, the velocity of fluid, actually the what is called the energy level in a stream flow is equal from place to place. So either the pressure difference basically is what it makes the water flow. But then if the pressure is less, then the velocity is more. Velocity is more, then pressure is less. So that way the fluid moves from one place to another.
Okay, that is actually, I think it's okay up to a point, but like if you want to refine it further, first of all, see if anybody asks you what is Bernoulli's equation, so first thing that you should tell is it is a conservation of mechanical energy. So first of all, like the problem that happens with the Bernoulli equation is you study it by the name of the person or the scientist or mathematician that discovered it, and you forget that what it is. It is basically energy conservation equation, and that too mechanical energy conservation. What do I mean by mechanical energy? So basically, if some of you have studied thermodynamics, so in there we typically study internal energy of the system, right? But internal energy is typically how should I put it? So basically, like there are two types of energies. One is called as macroscopic form of energies, and another type is microscopic. So basically, mechanical energy interactions are nothing but the macroscopic interactions, and microscopic interactions are basically the internal energy, that is the function of temperature, etc., that we take in thermodynamics. So leave that. So in simple terms, when I say mechanical energy conservation equation, it gives, like, consequently you can remember it as since it's a mechanical energy, no relation to the thermal energy part. So basically, like let's say you cannot apply the Bernoulli equation when there will be like heat transfer to the fluid or from the fluid. So because when the temperature changes, there is some thermal energy interaction, heat transfer happens, and Bernoulli equation is only, basically it is a conservation of mechanical energy, so you cannot apply it when there is this thing what you say, there is a heat interaction, or else as well as I think my handwriting is not that good. Anyway, work interaction. So basically, you cannot apply Bernoulli equation in both these cases if there is heat transfer or thermal energy interactions, and if there is work interactions. So basically, what I mean is, when I say thermal energy interactions, that means there should not be any heat to the supplied to the fluid or taken away from the fluid. And when I say work interactions, there should not be any work added to the fluid, as well as, I mean, work done on the fluid, as well as there should not be any work done by the fluid. So then only the mechanical energy conservation is valid. And as you said,
So the work interaction is not very clear.
yeah, so maybe I can give an example. Let's say there is a pump. So you know what happens. Let's say there is one inlet pipe and there is one outlet pipe. So like there is cross. I'll take some points 1, 2, 3, 4. So one, like let's say this is the fluid flow direction, and you know that for to operate a pump we need to supply some energy, or let's say some work. The pump does some work on the fluid. So in this example, what I mean is you can apply Bernoulli equation between point. Bernoulli's equation is valid or can be applied between points 1 and 4. So basically point 1 is far from the actual pump, and point 4 is far from the outlet of the pump. But points 2 and 3, they are like you can consider them point like just at the entrance of the pump, and point 3 at the exit of the pump. So there you cannot apply this. There are two reasons. First, there is work interaction, and also there will be vortices, because the fluid flow will not be smooth there. So I'll tell you some assumptions related to the Bernoulli equation. There you can understand it. But this is what I meant when I said it is not applicable during thermal interactions as well as work interactions.
Clear, sir. Clear, sir.
Okay. So now, first of all, it is conservation of mechanical energy. And like, if you consider types of mechanical energy, there are three types. So as someone said, I think Pradeep only said, that there will be kinetic energy associated with the fluid. Then there will be potential energy. And then there will be pressure, or some may call it flow energy or pressure or flow energy. So therefore, if you see the Bernoulli equation that we study, it typically has three components. I mean, along with the assumptions that I'll just highlight now. But as far as this course is concerned, or maybe like as far as the assumptions that we are going to consider during this course, if you consider those assumptions, the Bernoulli equation basically boils down to the conservation of these three energies associated with the fluid. So now there are different ways to write down the equation. Someone may write it in the form of energy. Someone may write into the form of head, or someone may write it in the form of pressure. It doesn't matter. You should know that it is conservation of mechanical energy. There are like I'll show you. There are many ways to write the equation, and therefore people get confused. But it is my job to tell you that it is essentially a this thing, conservation of mechanical energy equation. Now, and if you are interested in the derivation of this equation, basically they take a fluid element along a streamline and do some physics and all. I can't do it here because first of all I have not prepared it, and it is not the part of this course also. But if anybody is interested in the derivation as to what and why this happens, why this equation is of this form, there are some lectures by Professor Suman Chakravarti on NPTEL only. I think it is one of the courses on fluid mechanics. He takes couple of them. There you can find it, I think. Or you can refer to any standard book. Maybe FM White will have it, or IG Curry will have it. So if you are interested, that is completely optional. No need to. If you don't, that is also fine. There is no compulsion here. But I'm just saying, if anybody is enthusiastic enough or interested enough, maybe you can go there. But we'll come back to the final form that we are interested in. So basically, uh, I'll write the form that we typically use, uh, because the thing is, let's say we'll first highlight the assumptions. This is very important because if you attend any interview, technical interview after GATE exam or ESE exam, and if you say fluid mechanics is my one of the favorite courses, then rest assured they will either ask you questions from the boundary layer or pipe flow or Bernoulli equation. Typically, they don't go in the turbulent and other things because they themselves have forgotten by that time. But Bernoulli equation is quite a favorite topic in interviews because of these small nitty-gritties that students tend to forget over the period of time. But nonetheless, it is very important. So there are some important assumptions that you should remember when you write a typical Bernoulli equation. Uh, it can be, okay, I'll just write the equation. 1 second, then I'll write the assumptions. That will be better. So here I said it can be written as this thing, right? Energy. So basically, kinetic energy, you can write it as 1 second. Yeah. So kinetic energy, if you just write it per unit mass, it is v square by 2. And if you write potential energy per unit mass, it will be mgh is typically the potential energy formula, but per unit mass, if you write, it will be just gz. Z is the height from the datum. And then the pressure energy, if you just match the units, you'll realize that if you want to write it in the form of energy per unit mass, then it takes typically this form. And C is a constant because, as I said, it is a conservation equation. So this sum of these three quantities for a fluid flow between any 2 points should remain constant under some assumptions that we'll discuss. Somebody can like come and express this equation in the form of head, which is typically done. So that is basically head or energy per unit weight. So if that is done, so basically they divide the whole equation by uh, g, gravity acceleration. So then it becomes v square by 2g plus z, and then p by rho g is equal to c. So then they call this as a uh, you know static pressure head, static pressure head. This is your datum head, and this is your dynamic pressure head. So you can write it in any form, but in the end it's a conservation of energy equation that you should remember. And one important term, this static pressure head plus datum head, they are typically called as piezometric head. These are all terminologies, you should remember them. And I think static plus dynamic, they call it stagnation also. Yeah. So I'll just make a separate arrow. So if you consider these two, static plus dynamic, it's nothing but the stagnation head. So these are different terminologies that they use. You should be aware of them because in problems they typically directly give you piezometric head, stagnation head, and if you don't know, then you can't solve the problem. That's the drawback there. But anyway, now what all the assumptions that go behind these equations? Uh, I'll write general form of Bernoulli's equation.
Sir, one question. Like, suppose in the borewell or tube, the water level is basically jet plus rho by the geometric head, is it not?
Okay. Okay. It depends. I mean, where is your datum? What is your reference for the
Mean sea level.
calculation? Sea level.
Yeah.
Yeah, if you consider sea level as your datum, then there will be this datum head also will be there. Whatever is the height of your home from the sea level, that you should consider. And then what is the static pressure head there? Because depending on height, static pressure head also varies, right? Atmospheric pressure varies. Assuming it is open to the atmosphere. So yeah, that way also you can consider. So basically, so general form of a Bernoulli equation you might have seen in the class. It is, there will be one unsteady term, then there will be pressure term, then there will be velocity term, and then there will be datum term. This is the differential form of the equation. So typically, I'll just write it. This is a differential form of Bernoulli equation. For problem solving, this may not be useful, but to understand this thing, what you say, what, like how you derive the equation, this is the differential equation form. Then they typically integrate it. So integral form between, let's say, you need 2 points 1 and 2. So this will be integrated from 1 to 2 along the streamline, and there also from 1 to 2 you will integrate the pressure term. Then there will be this velocity and datum are basically properties of the system, so directly you can integrate them. So it will become v2 square minus v1 square by 2 plus g z2 minus z1 equal to the integration of constant will be some constant, because then if you divide that, if you differentiate a constant, you will get 0. So this is the integral form. And like for these forms, these forms of equation, we consider fluid flow to be, first, it is assumed as frictionless or inviscid. So there is basically no viscosity. In reality, there is no fluid which will have 0 viscosity, as we discussed in our initial classes. But this is some sort of idealization, and in reality what they do, they assume no viscosity initially between 2 points. They solve the problem, and after solving they say that okay, we assume no viscosity, but in reality there will be some viscosity, so we should multiply the final result with some factor that accounts for the viscosity. So basically, if you have gone through the, if you had gone through the flow measurement devices classes, so like there they solve the whole thing assuming no viscosity, and finally they define some coefficient of discharge parameter, which is the actual flow rate divided by theoretical flow rate. And theoretical flow rate you solve using these idealized equations that we are writing now. But in reality, it will be lesser than the ideal equations or idealized equations because of the assumptions of no viscosity. and since there is a viscosity, the flow will be lesser. So therefore, coefficient of discharge is always lesser in flow measurement devices, less than 1. Sorry. And this integration, since we are doing, yeah. So one more. Therefore, yeah, this is very common. Since this assumption is there, therefore, Bernoulli's equation cannot be applied within a boundary layer. Anybody knows what boundary layer is? We have not covered so far in this class, but it is a part of this course. It will come later. Anybody knows what boundary layer is?
So the surface of the stream itself is a boundary layer, and also the sides, they are boundary layers. The sides of the stream of the river.
Yeah. So basically, let's consider one surface over which fluid is flowing. It may be liquid or gas. What happens? The first layer sticks to the surface, then second layer of fluid particles slides over the first layer of the fluid particles. Like that, flow takes place, right? So near to the solid surface boundary, there is a small region where viscous forces, the viscosity of the fluid, is dominant, and that region is called as boundary layer. We will discuss this in details in the later classes, but just keep in mind that since there the viscosity terms or viscosity effects are highly dominant, we cannot apply Bernoulli's equation there. This is very common question asked in multiple uh, competitive exams where, you know, not subjective exams but objective, like GATE or ESE prelims, CSE prelims, etc. So there you should keep in mind that you cannot apply Bernoulli equation in the boundary layer region. And also, as I was saying in this pump example, since in between point 2 and 3, uh, there will be rotation of the fluid, so there will be some viscosity effects along with the this streamline assumption is not valid, and that I will tell you. So therefore, just keep in mind that Bernoulli equation is very idealized equation. You cannot apply it anywhere and everywhere. Uh, I mean, some people do, and they get some answers in, like, and some answers may match, some may be within some error. But strictly speaking, you cannot apply that in uh, boundary layers. Then there is second assumption is there, which is fluid flow along a streamline. So streamline is basically anybody knows what is streamline in a fluid flow? Anyone? Nobody?
The flow path.
So I think it is a straight line path.
Okay. Anyone else?
The fluid particles, sir, they move at the one line, like the stream flow. There's a like laminar layer kind of thing.
Yeah. So so basically, streamline is not a straight line always. It can be a curved line. It only says that by definition, streamline is a line in which the points of that line, uh, if you consider a particular point on the streamline, I'll just draw some simple streamline. So if this is a streamline, and if I consider any point on this streamline, if I draw a tangent to the line through that point, this will give me the direction of the flow at that point for uh, that particular time. If I draw, if I take some other point, and if I draw tangent there, I'll get direction of the flow in that at that the point at that time. So fluid flow along a streamline, it is actually since we have not covered fluid kinematics, ideally fluid kinematics should be covered before fluid dynamics, because there you would have been introduced to the term streamline, streak line, path line. Path line is the one which you guys were saying. So if you consider one particle in the fluid, and if you trace its path at various instances of time, then you will get one line, and that is called as the path line, which is actually a path followed by the particle. But streamline is a different thing. Streamline is essentially a line on which it is a locus of all the points on a line, and if you consider any point on that line, and if you draw a tangent to the line at that point, you will get the flow direction at that point at that time. So fluid flow along a streamline is the assumption. Why? Then only you can do this integral. From differential form, if you want to come to the integral form, you have to do the integration between any 2 points, right? So there you need to assume that these 2 points lie on a streamline. Then only you can do the integration. Otherwise, you can use the differential form without the second assumption also. If your fluid flow, 1 second. No, you can't do that because the derivation is of that sort. So forgive me for confusing, but you need this assumption for this derivation. And the consequence of this is, first of all, therefore, you cannot apply Bernoulli equation in turbulent flows, because in turbulent flow, you know this, that the streamlines are, what you say?
So you explain one's buffer zone where we'll explain turbulent flow. So I think that is I think the inviscid surface flow zone.
No, inviscid means the viscosity effects are negligible. That will not happen in turbulent flow anywhere, because in the laminar sublaminar layer, which is closer to the surface in turbulent flow, there are viscous effects. In the buffer layer, there are smaller viscous layers, but the fluid mixing is very rapid. It is not a laminar flow, it is a turbulent flow. So in turbulent flow, anywhere you cannot apply Bernoulli equation. So in laminar flow you can, because laminar flow can be considered as a fluid flow along a streamline or a bunch of streamlines, which is they call as stream tube or something, but not on the peripheral region. And in turbulent flow, so it is big no. So because of this assumption, this equation is not applicable for turbulent flows. And also, since again we have not introduced to the concept of rotational flow, irrotational flow.
We have studied about it.
Okay, but I have not taught and I have not seen in the course syllabus covered so far. I agree that you might have studied from somewhere else, but
No,
anyway.
here I think the sir told us in one of the lectures, rotational, irrotational. Yeah, I think there are some problems also here.
Okay, then that's good. But essentially, what happens? This assumption, they're like because of this assumption, there are two cases that arise. So I'll just draw a simple arrow here. So when I say the Bernoulli equation is valid when the fluid flow is along a streamline, or the equation is applied along a streamline. So there are two types of flows: rotational flows and irrotational flows. So basically, rotational flows, that means between, like, it is that type of fluid flow in which, if you consider two fluid particles in a fluid flow, there will be some angular velocity or some angular acceleration, some sort of angular interactions will be there. rotational. But in case of irrotational flow, even if the flow is rotating as a whole, but there will be no relative vorticity or relative angular interactions between two fluid particles. So that is irrotational flows. And in irrotational flows, Bernoulli's equation is applicable across the flow domain because it is the property of irrotational flow that there will be no vorticity between any streamlines. So instead of taking one streamline, you can take all streamlines and across them you can apply Bernoulli equation. But in case of rotational flows, Bernoulli's equation is only valid along a streamline. So if somebody asks you in any exam or any interview that can I apply Bernoulli's equation for a rotational flow, then your answer should be yes sir, you can apply it as long as the the flow is the flow that you are considering is along a streamline. If it is not along a streamline, you cannot apply it in the rotational flow domain. But if it is a irrotational flow case, then you can apply it along any streamline or across any surface also directly. So like that. Then, so based on these two assumptions, we arrive at this differential in the integral forms, and then we further simplify this equation. Then further we assume first steady flow. So as I explained in previous classes, when I say anything is steady, that means the variation with respect to time will not be there. Therefore, the first term goes away. So this term 1 to 2 del V by del T ds goes to 0. Then again we assume incompressible flow. Therefore, your density is not a function of pressure, and therefore this integral where you have del P by rho between 1 to 2, you can take the density out and it becomes del P from 1 to 2, which is basically P2 minus P1 by rho. So you assume that the flow is incompressible, and that see basically this assumption says that your density is not a function of pressure. But I can tell you again, here is also one trick question that typically is asked. So one second. So this density not a function of pressure. It is true for incompressible flows. There is no argument about it. But it is true for compressible flows also, as long as the Mach number is less than 0.3. Mach number is basically the ratio of velocity of sound in that fluid domain compared to the velocity of sound in air. So that is the Mach number. And this condition, there is a derivation behind it. It's not a random thing. Let me just give me 1 second. Let me check if I have the derivation with me, because I don't want to give something just like this, but I mean, I am aware of it that there is a derivation. I may not have it with me at this point, but it's there. So basically, the point I'm trying to make is the the refined equation that we are going to get uh, is applicable for incompressible flows, but it can be applied for special category of compressible flows also, where your Mach number is less than 0.3. Just 1 second.
So you mean to say you can apply Bernoulli's equation, the Mach number is less than 0.3?
Yeah, because
we can apply.
Yeah, we can apply as long as the Mach number is less than 0.3.
Yes,
yeah. In compressible flows, Mach number is very important because there you basically Mach number is a criteria to define how compressible the flow is. So till 0.3 we take it because till that point the density variation with respect to pressure is less than 5%, something like that, and therefore you can consider the flow. You can consider the density as a independent of pressure, and therefore you can do that. 1 second, I think. Yeah, I have the derivation. I'll just give me a second. Yeah, so actually we are going, the time is going fast. Anyway, so basically with these two assumptions and two assumptions earlier, the final form of Bernoulli equation that we are going to use is the final form of that will be let's say P by rho, or my P2 minus P1 by rho plus V2 square minus V1 square by 2 plus Z2 minus Z1 is constant. So this is the final form that we are going to use, but I hope I have spent some like not some more time on this. So the point was, I mean, I could have directly gone to the question solving, but I feel this is a tricky part in this course, or maybe tricky part of the course that you should know. Like, obviously, we'll solve some examples, no question there. But if you have some theoretical background behind it, it will be better. And coming back to this, we'll just quickly see how this is done, and we'll move on to the questions because we are already at 6:46. So basically, this thing, yeah. So basically, flow is considered incompressible if the change in the density is less than or equal to 5%. In case of liquids like water and all, this is always true. So therefore, the water flow like at normal temperature pressures is always considered as incompressible. But in case of gases, this is important because there is a density variation with respect to pressure as well as temperature. So as long as the density variation and this is density variation divided by the total density, that should be less than or equal to 5%, then we assume that it is a incompressible flow. And let's say this Bernoulli equation, if we apply between, let's say there is a channel like this, and we apply and it satisfies the assumptions of steady flow, non-viscous flow, incompressible flow, etc. So then but the catch here is your velocity at the point 2 is 0. So if such flow is taking place, and if you apply the Bernoulli equation here, what you will get, and when the velocity is brought to 0, it is considered as a stagnation pressure. So P2 will be equal to stagnation pressure. So as I told you earlier, this stagnation head is static head plus velocity head or dynamic head. So when the velocity is 0, whatever pressure that you have at the point, the static pressure will be equal to the stagnation pressure. So this P2 is nothing but the stagnation pressure at point 2. And if you apply the Bernoulli equation, it will become P1 by rho g, and let's say I'll take rho 1 plus V1 square by 2g plus Z1 equal to P2 by, let's say there is a density change, or let's consider rho 2g, V2 square by 2g Z2. And this is a horizontal flow, so Z1 and Z2 are equal, so that goes. V2 we are assuming as 0 at that point, so V2 goes. So what we have here is V1 square by 2 is nothing but P2 minus P1, or P2 rho 2 minus P1 rho 1, like that. So if you okay. Yeah, so this can be written as del P by rho. I mean, assuming rho 2 and rho 1 are not that different, so you can assume that their rho 1 is fairly equal to the rho 2. So then the denominator becomes same and the numerator is the delta P. Then what you do, you multiply both sides by this term, V1 square by V2 into 1 by d rho by d rho, d rho by rho, same this side. This is the earlier term. You multiply with the same term, so d rho by rho. Now what happens here? This term is v square by 2 into d rho by rho. So this is density change divided by the density. It becomes 1 by rho. If you take common, it is delta P by d rho by rho. I am just rearranging the terms, nothing separate. And this is what we called as K is the bulk modulus. Yeah, K. This is the definition of bulk modulus for a fluid, which we denote by the term K. And this thing, I'm just writing formula here because this Mach number that you may not be aware of, Mach number is, it is typically denoted by MA, or MA. It is nothing but velocity divided by the speed of sound in that medium, right? And speed of sound, there is a formula for it, which is in terms of bulk modulus, it's K by rho. There is also derivation for that also, but if you go there, it will take a lot of time. So for the time being, just assume, like, take the formula for the speed of the sound in any material as k by rho. K is the bulk modulus of that material or that fluid, in this case, divided by the density. So, so now we have this definition for C. We have this from this equation number 1. Let's say this equation number 1. We can get the V, this thing, what you call V, this thing. Okay, I'll just do it only. So basically, what you do square on the both terms, because in equation we have V square. So from equation 1, what is your V square? It is 2 d rho by rho into K. And one rho will be there. K divided by rho. And what is C square from this equation 2? It is K by rho. So basically this goes, and what you remain with is 2 into d rho by rho. Okay. So therefore, your Mach number is square root of 2 into d rho by rho. Okay. And as I said earlier, if this change of density, percentage change of density is less than 5%, it is an incompressible flow, or you can assume that density is not a function of pressure. Therefore, if you put 2 into 0.5% is 0.05, right? So this becomes square root of 0.1, which is 0.32 something. It is approximately 0.32. And therefore, if Mach number is less than 0.3, we can assume flow to be incompressible. Okay, so this is what I meant when I wrote in the red color here, that for a compressible fluid or even for a compressible flow, if the Mach number of that flow is less than 0.3, you can assume that the density is not strongly correlated with the pressure of the flow, and therefore you can assume it is an incompressible flow, and you can apply Bernoulli equation. So this is the proof. It is generally not told, but this is what it is. I hope it is like conveyed properly to you. Anybody has any doubt? I mean, this proof you can leave if you are not like if you are not fully on board with this. But I just thought, since I'm telling you something, I should highlight how it came. Anyway, as far as this class or the problem that we are going to solve next are concerned, there should be one G here. Sorry. Yeah, there should be one G here. I missed it. Yeah, because there is G with the Z, right? So there should be
Sir,
G here.
I have a doubt, sir.
Yeah, tell me.
You have written, sir, if Mach number is less than 0.3, we can assume to flow to be incompressible. And previously we have studied that true even for compressible flows with Mach number less than 0.3. So compressible flow will be incompressible flow will be in a less than 0.3 Mach number.
See, if Mach number, for incompressible flow, there is no concept of Mach number. So you don't consider Mach
Okay.
number for incompressible flows. Mach number comes only for compressible flows. And in compressible flows, if the Mach number is less than 0.3, you can consider it as an incompressible flow and apply the Bernoulli equation along a streamline in that flow.
Okay, sir. Thank you.
Okay. So now we'll move on to some problem solving, because
Sir, from this technician pressure, the pitot tube concept was there, sir.
pitot tube.
From this technician pressure that you consider, sir. Pitot tube.
Yeah. So basically, stagnation, as the name suggests, what do you understand when I say something is stagnant? So as the stagnant word itself means something is at rest. So basically what is done is, when the fluid is flowing, you do one thing. You put one L-shaped or 90-degree bend shape in, you dip it in the fluid, let's say till the center. So what happens? Water enters the tube and it will come to the rest, right? Because it cannot flow anymore. And therefore, since water is brought to the stagnation condition, the pressure that you get there is called as stagnation pressure. So in pitot tube, as you rightly said, the pressure that we get is stagnation pressure, because the velocity head goes to zero, and only therefore we get the stagnation pressure. And it is, stagnation pressure will be always higher than or equal to the static pressure, because by definition stagnation pressure is static pressure plus dynamic pressure, which is v square by 2, and velocity is always positive, therefore stagnation pressure will always be greater than or equal to static pressure. Any doubt?
No, sir, no doubt. But
Yeah, so no, I'm saying this because in some competitive exam this question is also asked, that like
sorry,
it is.
if you can the explain, sir, numerically, it will be great actually. Sorry, but it is, I know it is easy thing, but
No, it's okay. There is no need to say sorry or anything. So basically, what I'm saying is, as I told you, stagnation head is summation of static head, which is P by rho g, plus dynamic head. Sorry. Which is v square by 2g. Okay. So look at this term. Uh, we know that velocity is always greater than or equal to 0. It cannot be negative. It is, I mean, it doesn't make any sense. Therefore, the dynamic head, therefore, this v square by 2g, either it will be 0 or greater than 0. And therefore, what I'm trying to say is, stagnation head will always be greater than or equal to static head. So that is what I meant when I said it is important. Many a times students don't know what is stagnation, what is static head, and therefore uh, they get stuck in this kind of questions. But since you are here, I think it should help you that stagnation head is always greater than or equal to static head. It will be equal to static head when? Can anybody answer me? It will be equal to static head in when? The answer is
velocity 0 completely.
yeah. Can you give me one example when the velocity will be 0? Yeah, I mean any flow that is at rest is
So no
basically
slip condition will be there.
okay. Yeah, their velocity is 0, but I was talking about the flow velocity. Anyway, the answer should be, if your flow is at rest, it is not moving or the liquid is not moving, so there is no flow. In that case, your static head and stagnation head are equal. There is no change. So that is the limiting case. But typically, we study flow, right? So there will be some flow of fluid from A to B, and therefore there will be some static head, stagnation head, and this is the relation between them. So this is like 1 mark question in GATE or ESE prelims. Somewhere you can see this question also. Anyway, so now we'll move on to the problem solving part. So if you want, you can take some water break, because I am taking one. Let me just drink some water. I'll be back in a couple of seconds.
It's a 5 minutes break we can make, sir.
Yeah, 2 minutes break, not 5 minutes.
Yes.
We'll restart at 7:05. Okay. Yeah, so we'll start again. So now, like as I said earlier, the application of Bernoulli's principle is basically important for flow measurement devices. Like these are mechanical flow measurement devices. Like nowadays there are more digital sensor based devices, etc. But there was a time, and I mean nowadays also, if you are, if you have, if you want to go for a low cost flow measurement devices, these devices are used. There may be accuracy issues. So if you need very high accuracies, maybe you can go for electronics or pneumatic or digital or whatever. There are many types of sensors based uh, flow measurement devices. But uh, there is a class of flow measurement devices based on which operate like you can measure the flow using those devices and apply Bernoulli's equation, and you can get the flow values there. They are fairly accurate, not like up to like very high accuracy, but for normal applications they are quite useful. So keep that in mind. So there is one thing, one which is called as venturimeter. Then there will be something called as orifice meter, and I think one more was there. One second. Yeah, venturimeter, uh, orifice meter, and flow nozzle. So see, there like basically uh, the principle is same only, and I think venturimeter is only discussed in this course. Uh, so yeah, one second. So as I said, venturimeter is a flow measurement device. Uh, there are like couple of important concepts in this, which I will just tell you.
Sir, I have one doubt actually. I don't know, maybe I'm wrong actually. Like in pitot tube, sir, when you say velocity is zero, then you say that it is like it is representing that like v square by 2. How it is possible, sir? When we say v is equal to 0, then what will v square by 2? Like how v square rho by 2, how it will represent when v already is 0?
Uh, one second.
So that mathematically, so just a touch, like I don't know, quantitatively, if you kindly explain that, like concept of pitot tube.
Yeah, so uh, see, pitot tube, as I said, no. Uh, mm, so basically, how it looks is like this. So if there is a fluid flow, let's say there is a channel flow and you are looking at a cross-sectional area. This is the center line of the pipe. So what you do, you put one L-shaped tube here like this, and there will be small opening here, and what happens at this point, like if fluid is flowing in this direction, here will be some velocity, right? Because that will be the average velocity of the fluid flow at the center. Maybe if you are considering average fluid velocity, it doesn't matter where you put the petard tube, because that is the surface area average and it should be constant everywhere. But typically it is shown at the center, again, because the fluid can be considered as inviscid fluid flow there. Anyway, that's not the point. So what happens? The fluid will travel through this tube. Initially it will be empty, and here it will start rising because it is open to the atmosphere, right? And if the pressure inside the pipe is greater than the atmosphere, the liquid level will be rising above the uh, pipe height. Anyway, above the ambient pressure. So here, uh, what happens? This head, this height that you get from center to here, it is nothing but your stagnation pressure, because uh, here, velocity is zero. Here velocity was not equal to zero, and at this point or at any point in the vertical column, velocity is zero. So you brought the fluid to the rest, and that is what the stagnation means. So therefore this total will be P by rho g plus V square by 2g, whatever velocity is your fluid is having. uh, so you will get the height of this column is nothing but static head plus dynamic head. Static head is P by rho g, dynamic head is V square by 2g. And what typically is done is, in practice, now see, your objective is not to find the stagnation head, because that is of no importance to you. You need to, typically you need to measure the flow rate through the pipe, and that is typically cross sectional area into velocity. So you want what is the velocity, you don't want what is the P by rho g plus V square by 2g. So this is your objective, to find V. So now what is done is, typically this is what is pitot tube is. Is it clear so far?
Yes, sir, but the concept of V is not equal to zero and V is equal to zero. That part is a bit difficult. Like, when you say stagnation or stagnant, like in movement of fluid, the velocity is zero. Is it
Yeah.
correct?
So at any point in this vertical limb of the pitot tube, there is no horizontal velocity, right?
Yes.
Because the fluid is brought to the rest. It is stopped.
All right. Okay. Yeah. Yeah. Got it,
And
sir. Yeah.
yeah, in practice, what is done is, there will be one annular tube around the central tube. 1 second. No, I'll not show this way. It will be confusing. So they put one more tube here, straight tube only. 1 second. So here also, fluid will start coming up, right? And if the pressure, and it will rise till the pressure at the top becomes equal to the atmospheric pressure.
Yes, sir.
Typically, this is called as a piezometer, piezometric tube or something. Piezometric tube. And here, the difference that you get is a static head, because it is open to the atmosphere. There is no velocity head coming into the picture here. So here you get P by rho g, and this should be till here. And this is P by rho g plus V square. So therefore, what you do, this is pitot tube. Therefore, you do one thing, you put piezometric tube, you put pitot tube as close to them as possible. We don't want much variation. And then you take the difference of the two readings. So if this is a reading H1 and this is reading H2, Then h1 minus h2 will give you v square by 2g, right? And therefore your velocity that you want is your parameter of interest. You'll get like this, and therefore then you can do q equal to av. So this is how they get the velocity, they get the flow rate using pitot tube and piezometric tube. But in reality, there are no separate two tubes. What they do, they put two annular tubes together. Maybe you can Google it, because carrying two tubes is a problem. So they put the both tubes in one component only, and that is called as pitot static tube. Working principle is same. There is no change there. There also you will get two separate readings. You take the difference and you multiply with 2g and take the square root. That is your uh, velocity of the flow. You can Google it. It's very commonly used. You'll see the picture and you'll understand. So this is the pitot tube uh, and the flow measurement thing. Uh, then there is one more thing I want to discuss. 1 second. Which is actually very frequently asked. 1 second. So, like there is one this venturimeter coefficient of discharge, etc. That is there, and one thing is there. Let me just quickly see if I can find it. People get confused there, and rightfully so, because it's slightly thoda important concept here. So basically, I'm not able to find it. Yeah, so 1 second. I can take question only directly. Yeah, so again, this type of question is very commonly asked from this parties. There will be a pipe through which a fluid is flowing. Let's say this is the center line, and what they typically do is they put this pitot tube like this, and again maybe I should have taken the image to draw it. It takes time. Anyway, forgive my drawing, but this is how it should look, and this is your pipe. So yeah, and the flow direction is like this. And what happens, they put if this is water, they'll put some mercury or something here. There is another variation also. Instead of putting, so mercury is a denser fluid than the water, so therefore there will be the levels will be like this. And this is the difference between the two readings. And now again, your objective is to find the flow velocity and flow rate through the pipe using this device. So in this case, what you do, one second. Yeah, so from our this class, what you say, and let's say this is the datum, just to make our life easy. And this will be the, let's say this is 0.1, and this is 0.2, and the distance between 0.2 and the mercury level is what do you say, y2, this distance is y1, okay. Let's say the density of mercury is rho m, and density of water is, let's say, rho w. So we assume steady, incompressible, inviscid flow, all the assumptions that are required. But even before that, even before applying the this thing, what you say? Actually, I should explain this in the context of venturimeter only. I am putting it in normal pipe. Anyway, I have to redraw. No issues. So for this case only, there is no need for a datum or anything. This is our fluid statics class revision we can consider. So now, so let's like from fluid statics. Here, see the pressure at this interface is equal, right? Because uh, it is the same liquid and same height. So therefore, you can revise and write the this thing, what you call uh, P1, which is the pressure at point 1, plus rho water into G into Y1 plus rho of mercury into G into Y is equal to, yeah, and yeah, this complete height is not Y2, it should be here only, because otherwise it doesn't make any sense. One second. Y2, Y1. I should delete this Y2, Y1. It is causing confusion. Anyway, yeah, so can anybody help me out here uh, from our previous class? Mm, okay, I can just define some one length only. Why am I doing it this way? Let's say this distance is some y1. So P1 plus rho WGY1 plus rho MGY1 GY of mercury will be equal to the P2 plus, now it is total water here. So it will be rho W G into same Y plus Y1 because it's completely water here. So it will be Y plus Y1. This is from our fluid static class, okay? So no need to worry about it. Now we need to eliminate Y1 from this equation, right? Because that is our construct. Okay, if we solve this, what happens? Rho W Y1 will get cancelled. P1 plus rho m gy is equal to P2 plus rho w gy. Okay. Yeah. So then you do one thing, we need to take the y out, right? So P1 minus P2, it becomes, or maybe P2 minus P1, because uh, from the figure P2 is greater than P1. It becomes rho m minus rho w into gy. Therefore, your y is P2 minus P1 by rho, sorry, rho m minus rho w into g. Correct only, no? I think it is correct only. But P1 by rho g. Then, yeah, so this leave it at this point like this only. Then they define something called as a piezometric head between 1 and 2. I told you earlier, piezometric head is nothing but P1 by rho water G plus Z1. This is piezometric head at point 1, and 1 second. Rho mgy P2 rho gy2. It should not be this way. 1 second. Y2. Okay, let's see how, where does this go. P2 by rho wg plus Z2, something they call as H2. Here Z1 and Z2 are same, so it should not matter. So basically what we are interested here is P1 minus P2 by okay, but here we have got y in terms of, let's say this is equation number 1. So what we can do, we can modify equation number 2 or equation number 1 also, it doesn't matter. So yeah, we can put P2 minus P1 from equation 1. So it should be rho w minus rho m into y into g divided by rho wg. So what I have done is I have taken P2 minus P1 from equation 1 and put it into the H equation. So Gg gets cancelled, and therefore what you get is H is equal to yeah, it should be actually between point 1 and 2, right? So it should be P2 here minus P1 Z1, because when I say isometric head between any 2 points, it's difference of the last point minus first point. So here it should be P2 minus P1, and again it will be rho m minus rho w. So if you just simplify, it becomes rho m by rho w minus 1 into y. So this is the y is your manometer reading, and h is your piezometric head. So this derivation itself was asked in multiple ESC prelims and gate exams. Now, okay, you may ask, why do we have to do all this? Why do we need this H? Because first of all, let me clarify one thing. Here we have considered horizontal pipe. Therefore, this Z1 and Z2 did not play any role. But if the pipe is inclined or something like that, then this summation of P by rho g plus Z, the piezometric head, that is the important concept. Therefore, I have written it in this form here. If you would have noticed, and therefore, one thing that you should note that is, instead of this horizontal pipe, if I take, let's say, pipe inclined at 45 degrees to the horizontal, and if I do this algebra for that pipe also, I will get the same result. So this result is independent of pipe orientation. That was also one of the questions that was previously asked. And now independent of orientation of this pipe. So in this question, we are considering pipe horizontal, right? Completely horizontal in this derivation. But if you consider this pipe as, let's say, at 45 degrees to the horizontal, then this H becomes, this Z1 and Z2 are not same in that case, right? There will be some difference there, and that will compensate for the static part of the equation. Maybe you can take it as an exercise. Consider a pipe at, let's say, 45 degrees to horizontal, and if you do this calculation, what you'll realize is you get the same answer. And you should, because you're considering piezometric head here, and piezometric head is basically summation of static head plus datum head. And uh, datum head, let's say if the pipe is horizontal, your datum will be constant, but if it is vertical, or not vertical, if it is inclined, your datum head between point 1 and 2, which is Z1 and Z2 will not be same, but summation of P2 by rho Wg plus Z2 and summation of P1 rho Wg by plus Z1 should be, compensate for the increase in datum. So basically, what I'm trying to say is, if pipe is like this, if this is your point 1 now, and this is your, let's say, Z is equal to 0 datum, and this is your pipe 2, point 2. So this is 1, this is 2. Now, and this will be your Z2, right? Here. And this one will be, let's say, here, your Z1. See, V1 equal to V2, okay, because area is constant. So from mass continuity equation, V1 is equal to V2. Therefore, Bernoulli equation will be reduced if you assume that the flow is steady, etc., and all the assumptions which are required for the Bernoulli equation application. I'll just write, since A1 is equal to A2, which is cross-sectional area, V1 should be equal to V2, right? Velocity should be constant through this pipe. Therefore, if I write Bernoulli equation, one second. Yeah, so P1 by rho g plus Z1 will become P2 by rho g plus Z2, right? And since Z2 is greater than Z1, therefore P2 will be less than P1. So your pressure at point 2 will be less than P1. And therefore, when you do this, when you put some manometer there and if you check this Y level and all, no, there you will get Y formula, which is equation 1, like that in a different form. And when you finally do the calculation of H, you should get it in the same form, is what I'm trying to say. So basically, when the velocity is same through the pipe, if your datum increases, your static pressure will decrease at that point. Like that you have to consider. Anyway, so coming back to this one, this is very important result, H equal to rho m minus rho w minus 1 into y. And why? Because so then based on this, basically you calculate velocity. 1 second. This part I am not, 1 second, I am just looking there. So you get H, right? So manometer reading is different from your piezometric head. So when you have H, now your objective was to find the velocity through the pipe, right? So they just do that V equal to under root 2gh, but I am just looking, 1 second. P2 minus P1 by, yeah, so if you consider V as the velocity through the pipe, so if you write again Bernoulli equation, since Z1 is Z1, Z1 is equal to Z2, what you will get is 1 second. P1 by rho g HS, ठीक है. Yeah, so basically what they do is they equate whatever is the pressure drop equal to V square by 2g, the flow velocity through the pipe, and therefore essentially basically if you want to get the velocity, you just do root 2gh. So piezometric head difference, the reason why we do this calculation is we get the h value from the manometer reading, and therefore you just do V equal to under root 2gh, then you get the flow velocity, average flow velocity, and if you multiply it with the cross sectional area, then you get the flow rate, which is your objective. So like that this goes. One second. Yeah, so I mean you can solve some problems on this, but this is the derivation. And I'll take one example which I found very interesting. It was, I think, previous GATE exam question only. So what they did in that question, let me just get to the question. Yeah, it is 2003 question, 2 marks. So they have arrangement like this. It is like a Venturi meter only, but it was a smooth. I'm drawing slightly different. There was a small outlet here. So instead of putting some manometer or anything, it was like this. So there is an average flow velocity U through this pipe. This is a pipe. And they have one spring, like one piston is there, and it has a spring. Yeah, it is actually slightly different. So the spring is slightly compressed when the fluid is flowing, and this distance, which is the compression in the spring, is what they have given as x. The spring has the spring constant of k, and it is grounded here. So what is happening basically, initially when there was no fluid flow, the spring was at, at its natural length, so there was no deflection, x was 0. But when the fluid flow started, since the cross-sectional area is reduced here in this small region where the spring is attached, uh, you know that this thing Z1 is equal to Z2 because it is the horizontal pipe, right? So only pressure and velocity terms in the Bernoulli equation are there. So when the cross-sectional area reduces, the velocity will increase because your flow rate is constant. So when your velocity increases, your pressure will decrease at that point, right? One second. The spring should not get compressed. It should get elongated actually. Maybe I have not drawn it properly because the pressure at that point will be lower, right? Yeah, so basically spring is not compressed. Uh, Spring will get elongated. My bad. Earlier I had drawn properly. Let's say, or yeah, so only I had to change the x. So spring is not compressed, it is elongated. So let's say earlier it was here and now it is here. So this is the x. So now, okay, so this one they have given as this dimension as dt and this as capital D. What else is given? Yeah, and surface area of this piston as the d. The diameter of that piston attached to the spring is ds. So now this is the question, and what they are asking is the air is flowing through the pipe with the density rho, and the outlet pressure is atmospheric pressure. It is given in the question, PATM. Derive an expression for x. This is what they have asked. There are four options were there. I am not giving the options because otherwise it will take a lot of time. And that is not the point of this exercise. What you can do is look at the question there, you'll get it solved everywhere. But I'm just trying to give you some sort of different kind of flavor to the problems that are asked in this type of problems from this area. Well, let's consider these 2 points, 1 and 2. Now, from continuity equation, we have what do we have? Yeah, so since same amount of fluid is flowing from point A to point 1 to point 2, mass should be conserved. So your volume and the density is same. It is given that there is no temperature change. So density is assumed to be assumed to be constant. So flow rate, volume flow rate will be same. So that means A1 V1 equal to A2 V2. Now what is A1? A1 is nothing but pi by 4 dt square into V1 is equal to pi by 4. A2 is capital D square into V2. Correct. So this pi by 4 goes. Therefore, dt square V1 is equal to d square V2. Okay. So this is the one equation that we have. So we can modify it as V1 equal to capital D by dt square into V2. Now, here only you should get the idea. Since d is greater than dt, d by dt is greater than 1, and therefore V1 is greater than V2. Which I was saying earlier, that since the area is contracting at point 1 and then at point 2 the area is larger, uh, there should be the velocity at point 1 should be more than the velocity at point 2, which is again proved from using continuity equation. Okay, so that is there. Now what next? Then we apply Bernoulli equation.
No, sir, because sir, it is actually, sir, the pressure is less here. The velocity should be more, is it not?
No, it should be other way. It should be since the velocity is more at point 1 compared to point 2.
Yes,
Pressure should be lesser at point 1 as compared to point 2. Okay, so actually it was given in the question that you can apply the Bernoulli equation here. So I have written in the bracket that with all the assumptions that we discussed initially, we can apply Bernoulli equation here. So now we have P1 by rho g, V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2. And since it is a horizontal arrangement, Z1 is equal to Z2. Therefore, P1 minus P2, one second, P1 minus P2 by rho g is equal to V2 square minus V1 square by 2g. Gg gets cancelled. Therefore, P1 minus P2 is equal to rho into V2 minus V1 square. So this much also we have. Now in the question, it was mentioned that the average flow velocity is u. So basically, V2 is nothing but u, just a change of symbol. So if you put here and like from equation 1, what we have, V1 is d by dt square into u. V2 is u now. So therefore, P1 minus P2 becomes rho into V2 is nothing but u square minus V1 square, it becomes d by dt. Square was already there, then again we are squaring, so it becomes power 4 into u square. So if you can take u square common, it becomes 1 minus d by dt power 4. Okay. So yeah, so this is your P1 minus P2. Now, so what is P1 minus P2? The difference, pressure difference between point 1 and point 2. So this pressure difference is causing the deflection in the spring, correct? And since, okay, I'll write it here. Okay. See, this was not asked in the question, but I am giving you some physical intuitions so that you will get what is happening in this problem. Since d is greater than dt from figure, this means d by dt is greater than 1, right? And therefore, if you take fourth power of this ratio, it should also be greater than 1. And therefore, 1 minus d by dt power 4 should be less than 0, right? So this term here is less than 0. And therefore, P1 minus P2 is less than 0. Therefore, P1 is less than P2. So, P1, which is the pressure at point 1, which is the smallest cross-sectional area, is less as compared to pressure at point 2, which is atmospheric pressure. So, P2 is nothing but the atmospheric pressure. So, at P1, the pressure is below atmosphere, that we should remember. And therefore, the spring will be elongated. So this can also be one question, that if this is the arrangement, what will happen to the spring? Will it get compressed? Will it get elongated, or will it stay neutral? That can also be one question, 1 mark question. Anyway, so now we know that since P1 is less than P2, the spring will get elongated. And now we do the force balance for the spring. So by force balance for the spring, we know that spring force is, the spring force comes because the spring is getting elongated, and the elongation is happening because of the pressure force.
So there is a similar problem, sir, in the recent our assignment. I've written in the chat box.
Oh, I did not check the assignment today. Is it the same or similar? 1 second. But anyway, we have taken the problem. We are almost at the solution. Now we can't change it. 1 second.
Pressure is recovered, sir. What you're telling me, like pressure was less earlier because of divergence. It can be recovered. Yeah.
Yeah, see, this P1 is less than P2 will be same, because it is nothing but a instrument like a venturimeter or orifice meter. So till this point it should be same, but since there is new thing which is a spring, therefore this problem caught my eye. So anyway, now here spring force is nothing but it is usually minus kx. And now what is the pressure force because of the air? It is nothing but pi by 4 into ds square. What is ds? Ds is the cross sectional area of this piston, which is attached to the spring. And what is the pressure difference across this piston? It is P1 minus P2. So now it is just a exercise of putting these expressions in the place, and you will get the answer. So P1 minus P2 was rho u square 1 minus d by dt power 4. And it is asked what is k, what is the expression for x. So basically k will come this side and will multiply with the minus 4 side, both the sides. So it will become ds square rho u square by k, and it will become d by dt power 4 minus 1. So here also you can, oh, 1 second. Here also you can see this d by dt power 4 is greater than 1. So this bracket itself becomes greater than 1, and therefore x is positive. So again, that proves that spring gets elongated. Anyway, I mean, this is what it is. This was like slightly different problem than the conventional problems that you'll solve from this section. You will be able to solve most of the problems with this derivation. And again, you know, in case of since we are running out of time, in case of this venturi meter and some other orifice meter, nozzles, etc., what you do, so basically instead of this spring here, you connect the manometer. One end will be at the smallest cross sectional area, another end will be at the normal pipe diameter, and then there you will get some manometer reading, that is nothing but this y value, and then you get the this piezometric head difference using this formula, and then you get the flow velocity using under root 2 gh, and you get the q equal to av. But as I said in the beginning of this class, this is under the assumption of various assumptions, and one of them is that the fluid is inviscid, or there is no viscosity in the fluid. But if you consider water or air, it will be always viscous. So therefore, what you do, you define something called as coefficient of discharge. Discharge. Typically, it is called as CD, which is defined as Q actual and Q theoretical. So, and Q theoretical is nothing but what we got from our earlier calculations, which is Q equal to AV and A into root 2 GH, you know. But in actual, it will be lesser because viscosity is there for any practical fluid. Therefore, CD, no, I should write it this way. 1 second. Since practical fluids have viscosity, Q actual will always be lesser than Q theoretical. Therefore, CD will always be less than 1. This is also again one question asked in some competitive exams. So this coefficient of discharge that you define is also a number which will always be less than 1 and greater than 0. It should be as close to 1 as possible, because then you are going to the theoretical limit. But in practical case, it is, I think it is typically 0.6 to 0.8 in case of venturimeter. Anyway, so the point I'm trying to make is, even if I have not taken any numerical example because of the time constraint, I have list of problems here, but I have given you the framework how to solve this, and you can go ahead and solve the numericals based on this discussion. I am hoping that you will not get stuck anywhere. Maybe I have not taken like exact derivations and all, but it should be solvable. If you can refer to any standard reference book, you'll get the hang of the formula. And I would advise not to remember the formula, because you will forget them in the exam anyway. If you understand the concept, that is more important, is what I feel. Anyway, so we can stop here because it's already 8 o'clock. If you have any questions, you can ask me. I would urge you to go and solve some numericals based on this part. I hope you will be able to. And if you have any doubts, you can always ask me in the next class.
So there is a question, a similar question this time. The chat box, if you see.
Okay, Pradeep N has put some question in the chat box. The difference in mercury level of a pitot static tube connected to a submarine is 25 centimeter. Okay, assume the coefficient of velocity as 0.97. What will be the speed of submarine if the specific gravity of seawater is 1.019? So okay, we'll take this question. I am Pradeep.
If you have time, sir. If you have time, sir. Otherwise, not a big deal.
Yeah, I'll just briefly solve this. Maybe you can see the question in the chat. But question is something like that. You have a manometer, or let's say this pitot static tube. I don't know how you can put pitot static tube in a submarine. Because one end of pitot static tube should be open to the atmosphere, right? Anyway, I'm assuming it is manometer or something like that. So in question it is given that why is the reading of the manometer is 25 centimeter. So let's say it is 0.25 meter. And mercury is there. Density of mercury is 13,600 kg per meter cube. Here something called as coefficient of somebody's mic is on. Can you please mute?
Mine, sir. It is mine. Yes, sorry.
5 minutes. So there is something called as coefficient of velocity given in this question. Before going there, I'll just briefly tell you what it is. So basically, we are writing Q as AV, right? So there is coefficient of discharge parameter associated with the Q, and there is something called as coefficient of area parameter, which is associated with the area measurement, coefficient of velocity parameter, which is associated with the velocity measurement. So basically what it means is, as I'm saying that actual flow rate will be less than the theoretical. In the same on the same lines, actual velocity that you calculate will also be lesser than the theoretical velocity because of viscosity and other boundary layer, etc. And the area that you measure may not be equal to the dimensions because of scaling or some other obstructions in the fluid flow domain. So therefore this relation is there. So it is basically coefficient of discharge is equal to the coefficient of area into coefficient of velocity. So here what this coefficient of velocity 0.97 means is the velocity that you would have gotten by doing this calculation. The actual velocity is 97% of it. That's it. And now density of seawater, let's say I'll denote it as SW, is 1019 kg per meter cube. Okay. Now to find velocity of submarine V. Let's say V. So again, I told you I given this formula, right? This formula here. I hope I am again this formula. It's H-wala formula. See, I am not convinced that it is pitot static tube. Because see, if it is a pitot static tube, the other end should be open to the atmosphere, and it is a submarine. So I don't think you can put pitot static tube in the submarine. So I am assuming this is as a manometer. So therefore, otherwise if it's a pitot static tube, the difference will be summation of pressure head plus velocity head, right? And pressure they have not mentioned at what depth this submarine is there. If it is near the surface, then it will be atmospheric pressure. Otherwise, yeah. So the question is not clear, I would say, Pradeep N. So I am going ahead and assuming the typical problem solving methodology. This may be wrong because the question is not clear. If you could send me the solution, or maybe the solution that we get, if it matches with your solution, then maybe the question writing is wrong, or maybe something else is missing. Anyway, we'll solve it.
The options given, correct? These are the options given.
This question is from the assignment, or?
Yes, sir. This was current assignment. Tomorrow is the last date. So I also got confused, so I could not solve it well.
See, strictly speaking, I should not help you guys, but anyway, we'll try. I am not convinced whether this question is completely correct. Let's see what answer we get. If you do, this is the formula, right? So if you do this way, it is 13.6 divided by 1.019 minus 1 into y. Y is 0.25. Can somebody help me with this calculation, or should I do it? Anyway, 13.6 divided by 1.019 minus 1 into 0.25. This comes out to be 3.087 meter. Okay. Then the velocity, this will be theoretical velocity, will be under root 2gh. So 3.0 into 2 into 9.81 and square root of this. So this value comes out to be 7.782 meter per second, and actual velocity will be coefficient of velocity into theoretical velocity. So coefficient of velocity is 97%, or 0.97 into 7.782. So if you do that, 0.97, it is 7.55. 7.55 meter per
Yes, sir,
second.
it is there. So sorry, yeah, I wrote 6.82, so I think 7.7 is correct.
Yeah, so according to me,
I could not understand these questions very well. So
yeah, this question is not clear, to be honest with you. It's not your fault, because at one point of time they are saying it is a pitot static tube. Like, you can just Google it, pitot static tube. The one end should be open to the atmosphere, right? 1 second. Pitot static. Am I wrong? Maybe. Yeah, I mean, it's not necessarily open to the atmosphere. It can be connected to the flow itself. Yeah, I am wrong here. There is a variation of pitot static tube where the end need not to be open to the atmosphere. It can be connected to the pipe back. 1 second. If I can show you the image in my browser, you can all see my screen, right?
yes, sir, you can see.
Yes, I'll pitot static. Pitot static tube. Images.
So I was just looking for your email ID, sir. Then I found that you're a topper of the Pune So yes, sir, this school in the system. I got your name. I just searched your name, and
Oh,
it's just
yeah, yeah, it was long back. Yeah, I think it 10th result it was.
so it just flashed at the beginning itself. So
Yeah, yeah. One second, where did I see this image? Hmm. Yeah, see, as you can see, this pitot thing, it is still used in the aeroplanes or fighter jets, because this is like a fail-safe mechanism. Even if your digital system goes offline for some reason, this pitot tube will be, it's a mechanical component, right? It won't go off. It will be there. Anyway, there is one image I am not able to. One second. Acha. Oh, we are already 7, 10, 8, 10. Give me 1 minute. We'll just uh, 7 static pitot tube. It should be showing something now. Yeah. So see this image here. I hope you are able to see my screen. Yeah. So
yes,
I think this is the arrangement that they are talking about in submarine, because it is not clear in the question. Maybe they should have given any image or something. But I think this is what they mean. So there is a submarine, and uh, it is going with some velocity. So this nose of the pitot tube is outside the submarine. It is in the sea, facing sea. So uh, and this is the arrangement. So there is nothing which is open to the atmosphere, and this is similar to what we did, right? So this is the that y value that we derived one expression for, right? Here, where is it? So this h expression, I told you this is very important expression. 90% of the problems in this domain will be solved if you know this variation, and this is what I did. I just did h calculation, and then I calculated velocity as 1 root 2gh, and they have given some coefficient of velocity which is 0.97. So you multiply with the 0.97 and you get the answer. So like that, there will be another questions also. I am happy Pradeep has put this question, but I don't know whether I'm supposed to solve the assignment questions before
thank you, sir.
submission.
You just saved 2 marks, sir. I would have done no actually.
Yeah, yeah. No, no. See, I am happy to do it, but the NPTEL team says that you can't. Anyway, so at least you are attending the class, so you may get some advantage. That's fine. And Pradeep has put some other question also. One second. At the diverging section of the Venturi meter, the pressure and the velocity. Yeah. So as
That
I
you
did,
already explained, sir. You already explained this.
yeah. So in this question I explained, right? I think the question is answered here only.
Yes, sir. Yes, sir. Yeah.
Yeah. So if you have any questions, maybe we can take it up in the next class. But now that we are running out of time, so I think it's better we stop here. Uh, so shall we stop? Anybody has any questions or anything? Okay, then Pradeep, shall we stop?
Yes, sir. Yes, sir. Thank you, sir. Thank you so much, sir. Have a good night, sir.
Okay, thank you everyone, and see you next time. Good night. Take care.
Night, sir.
Bye.
Sir, you are very intelligent. You are very intelligent.
Uh, okay, thank you for the compliment. But actually, to be honest with you, uh, when I was studying during my undergrad and other competitive exam time, these concepts were not taught to me in one place. So, uh, I mean, what I am doing here is just I am collecting the information from various sources and making it in a single document or single lecture kind of thing. Uh, so I would not say I'm intelligent or anything. I think I have enough experience of competitive exams by now, so I know what works and what doesn't. So I try to bring the important things to the table. That is what I do, and other things I think you have to practice, then you'll get the hang of these things.
You will be a good professor, actually. A very good professor, sir. Once, like, doing PhD. Sir.
Okay. Thank you for your kind words, Pradeep. Let's see what happens. Anyway, for the time being, let's not jump ahead. We'll meet next Tuesday and we'll discuss next part of the syllabus.
Thank you, sir. Thank you so much.
Okay. Thank you. Good night, everyone. Bye.